I have just attached the link of the attendance form to you all. Please check in the check box. Okay, you may fill out the form now, and then the class code is also given. Okay, thank you. Okay, as from what I have counted here, I see some students didn't join the class, and then from the attendance form that I have here, I see that there are 2 to 3 students still haven't filled out the form. Okay, for student who just joined in, I have reattached the attendance form, the link, the link of the form to you. Please fill out the attendance form now. I will start the class shortly. All right. I see the all of you have filled out the attendance form, so I will start the class now. Today's lectures, I will continue with the chapter 2. Okay, the topics under the chapter 2 is about fabrication process and then followed by layout design rules. So today I will discuss, I will cover the layout design rules. Okay, this layout design rule is actually apply in the fabrication process. Okay, not fabrication process, it's actually before fabrication process. Okay, before we want to fabricate an IC, we need to design it using a software. Okay, in a layout form. Okay, so in the layout design, we need to verify whether it is correct or not. Okay, so the verifications that has to verify using the layout design rule. So today's I will talk about this, and then uh, the layout design rules. What is this layout design rules cover? Okay, what is this layout design rules do in the verifications? This also will be mentioned. Okay, why the layout design need to follow layout design rules? Okay, this will also be discussed later. Okay, so this is the PowerPoint that I have given to you. Okay, you can refer to my slide or you can refer to the copy that you have downloaded. Okay, layout design rules. It is the limitations of the patterning process given rise to a set of mass design guideline. Okay, we call it as a layout design rules. Okay, and then it contains a list of minimum feature sizes and spacing for all the masses. Okay, so this minimum feature size and spacing for all the masses is required in a given process. Design rules are a set of guidelines that specify the minimum dimensions and spacing allowed in a layout drawing. It allows not transition, this is translations. Okay, it allows translations of circuit, usually in stick diagram or symbolic form into actual geometry in silicon. Okay, so this mentions about the layout design rules after it has been successfully verified. The layout design rule, not layout design rule, the layout design will use to fabricate the IC based on the dimensions given. Okay, it can be translated directly using the dimensions given in the layout design rule. Um, uh, with the dimensions given, okay, the dimensions given, we can know, okay, if the layout design rule is lambda design rules, then we can actually make some translations, okay, from the layout design to the actual circuit, okay, to the actual geometry in the circuit. Okay, and then violating the design rules might result in a non-functional circuit or in a highly reduced yield. Interface between the circuit designers and fabrications engineer. Okay, a circuit designer usually is the person that designed the circuit or maybe produce the layout design of the circuit. Okay, and then the fabrications engineer, Fabrications engineer is the person that fabricate the circuit, okay, with the actual dimensions of the circuit based on the layout design that is designed by the circuit designer. Okay, so layout design rules act as interface for that purpose. Okay, layout design rules define ranges for features dimensions. Okay, the dimensions here included the minimum wire width. Okay, minimum wire width is the smallest dimensions permitted for any object. For examples, metals and polysilicon interconnects to avoid the breaks. Okay, so this minimum wire width, okay, as you see in the figure here, there are two figure. Okay, we see this figure first. Okay, this figure, the width, this is wire. Okay, we call it as layer, metal layer. Okay, so the layer must have a minimum wire width. It cannot be too thin and also it cannot be too thick. Okay, must follow a standard width, minimum width. Okay, according to the layout design rules given. Okay, and then another one is minimum spacing. Minimum spacing is the smallest distance permitted between the edges of two objects to avoid short. Okay, so you see this diagram, the spacing here is actually the spacing between two metal layer. Okay, we assume these two layers is a metal layer. Okay, so these two metal layer must have a minimum spacing. Okay, it cannot place too close to each other because we want to avoid the shock. Okay, so cannot be too close. Okay, if too close, then it will have a shock. Okay, short here means here the short here means the short circuit. Okay, and the spacing also cannot be cannot be too close. Just now I mentioned the spacing cannot be too close. Okay, and then the distance that it can place can be further. Okay, but that also depends on how far the spacing is placed. Okay, sometimes according to the layout design rules that we select, it can place further. Okay, can place further from each other between the metal layer, some cannot. Okay, but that we have to see. Okay, and okay, so this is the diagram. Another diagram. This diagram is the same one. Okay, as this one. Okay, just to illustrate to you in another form. Okay, so it's actually the same. These two are the same. Okay, you can see also with the two layers. Okay, these rules originate from the resolutions of the optical printing system, the etching process, or the surface roughness. Okay, here there are a few example. Okay, these examples are the examples of the layout design, okay, with the minimum spacing requirement, okay, given by the layout design rules. Okay, so as you see that this layout design is actually I copied from the electric VLSI software. It is a CMOS inverter. Okay, why I want to show you these examples because from the examples here, you can see the error. What is the minimum spacing requirement between the metal layers and also the active area in PMOS and NMOS. Okay, when you do your practical later, when you start to design your layout design for a component, okay, you will see this as well. Okay, so I mentioned here because I want you to take note that you can actually know, okay, what is the minimum spacing required between the layers, okay, when you design the layout design. Okay, so as you see that this is the first examples. This one is actually shows the minimum spacing between polysilicon to P active. Okay, polysilicon is actually this one, the red color layers. Okay, this one is a polysilicon. Okay, and then the P active. P active, this is the P active, this area. Okay, the whole thing here with the contact is the P active. Okay, so you see that this the white color is actually this part. Okay, this part is the part that I drag close to the P active. Okay, this one is when I drag, but I didn't place it near to the P active. Okay, so when I drag this polysilicon near to the P active, it will show an error. Okay, the error here is the polysilicon 1 to P active spacing is 0. Minimum is 1. Means that the spacing between the polysilicon and the P active must has at least 1. Okay, so if placed too close, there will be an error. Okay, if you didn't take note of this, when you perform the DRC, the rules checking, okay, you will get an error. Okay, so if you follow this, if you see the error, that means that you need to place further. Okay, place the polysilicon further from the P active, then it will not show any error when you do the rules checking. Okay, so this one is with error. Okay, this one is without error. Okay, as you see that this polysilicon is actually placed further away from the P active. Okay, compared to this is closer. Okay, but this is further. This is further. Why is that? Because as you see that the spacing here is 3. Okay, minimum 1. So the spacing is 3 means that it does not violate the design rules. Okay, so this one is correct. Okay, so you need to pay attention to this. Okay, it will help you to save time. Okay, when you try to troubleshoot your layout design. Okay, and then next examples shows the minimum spacing between well. This is not well. This is wait. This is okay. This is well. Okay, this is well to active area. Okay, so which one is well? Okay, we have P well, we have N well. Okay, so for this layout design, so which one is the N well and which one is the P well? Okay, to recall back, to help you to recall back, so this is the N well. Okay, and this is P well. Okay, this whole thing is the well. Okay, okay, maybe you wonder why this is P well and why this is N well, since the wells here is connected to PMOS. Okay, for this well, it is connected to PMOS, and then this well is connected to NMOS. Okay, if you go and study back again, uh, the wells must be different than the if you the wells the type of the wells here must be in a different type than the transistor that it then the transistor it will connect. Okay, so for NMOS it must connect to the P well. Okay, and then for the PMOS, it must connect to the N well. But for the active region, okay, active region is in this region. Okay, this is the region where we call it as active area. Okay, this one is active area. Okay, and active area for both of these PMOS and MMOS. For active area for MMOS, okay, this one is a P type. Okay, or we call it as P active. Okay, P active. And then for active area in NMOS, we call it as N active. Okay, you will have to identify and then differentiate what all this about. Okay, so here, the design rules, not design rules, this layout design shows the spacing between the wells and the active area. Means that this well and this active area. Okay, so you see that when this well and wells is placed very close to the active area, there is an error here. It shows that N active to P active spacing is 2, minimum is 4. Okay, so means that the well is placed too close to the active area. So the solution is we have to place it further. Okay, so you see this one is the one that is the spacing is 5. Okay, the N active to the P actives is 5. Okay, so this is the layout design. That is with no error. Okay, so if there is not show with an error, so means that this layout design rule is without error. Okay, so another one shows the minimum spacing between the active area. Okay, so between the active area means this active area, this active area and this active area, they are spacing. Okay, these two active area, they are spacing, and then these spacings, they are also minimum spacing between each other. Okay, so this active area, okay, when it is dragged, okay, the white color line here means that it is being dragged closer to another active area. Okay, so when it is dragged, it will show the error. The error here is P active spacing is 2.5, but minimum is 3. Okay, so when it is dragged closer to this active area, mean it is below 3. Okay, the spacing is 2.5, so it's below 3. So there is an error. Okay, so in order to make it minimum at least 3, the spacing, okay, we need to drag further, okay, further from the active area. So now the spacing is 3.5. So there is no error. So you need to check this. Okay, so these are the rules that must follow when we design the layout design. Okay, so another one is the minimum spacing between the polysilicon and the metal layer. Okay, so this is the polysilicon layer. Metal layer is the one that is in blue color. Okay, so how do we see this? How do we check the spacing between the metal layer and polysilicon? Okay, so if you try, you drag this polysilicon closer to this metal layer, okay, you will see the error here. Polysilicon 1 to N active spacing is a 0, minimum is a 1. Okay, I think I need to make corrections here. Okay, this arrow shows the minimum spacing between the polysilicon layers to N active spacing. Okay, so this is not between the polysilicon and metal layer. So I need to correct here. This is not the metal layer. This is the N active. Okay, N active means that this polysilicon and this N active. Okay, the spacing is between this spacing. Okay, let's see. Okay, so this is the spacing. Okay, here cannot show you because um, the polysilicon is drag. You see this white line? Okay, this is the polysilicon layers. Okay, and then this polysilicon layer is actually being dragged. Okay, the white color shows that it's being dragged near to the N active. Okay, and then when it is being dragged to near to the N active, it shows error. Okay, but if you compare with this layout design, this polysilicon layer, okay, there is a certain spacing in between here. Okay, here actually no spacing. Okay, I draw here wrongly. I shouldn't draw like this. Okay, you see that here there is no spacing. Okay, and then here spacing, there are spacing, but very small spacing. Okay, so this spacing is 1. Okay, the polysilicon 1 to N active spacing is 1. Okay, so it shows that from the N active or any active area to the polysilicon, okay, they must have a spacing. Okay, for this one, I think I can show you here. Okay, okay, I directly show you, okay, through the electric software here. Okay, this is the electric software. Okay, and okay, so what I want to show you directly because I want to show you how you can actually do it. Okay, so this one when you drag, okay, you can actually see that you see this one. Okay, when you drag, the whole thing is also followed. Okay, so we want to avoid this. So what we need to do is we need to okay, make sure that this one you see we need to make sure that the spacing is followed, okay, or else you see other components also will be mispositioned. Okay, and then the metal layer, okay, when you place near to the metal layer, okay, what we will get, okay, it seems like there is no error if this polysilicon is placed near to the metal layer, but when you do the root checking, they will still error. Okay, because you see that this is okay. This okay. Maybe there is an error, but I'm not sure. Okay, if you have this if you have this design and then you run the root checking, you have to see maybe there is an error, maybe there is not, but that depends on whether others layers they follows the design rules or not. Okay, but in this case, okay, the most optimized or the um, most without the most optimized design rules that is without error is like this. Okay, should look like this. They are properly positioned and then with a certain spacing. Okay, and then for width here for all the layers are standardized and fixed. Okay, so for the width for of the polysilicon and metal layer should not be a problem because all are fixed. Okay, all are fixed. What we need to ensure is we need to make sure the spacing between them they have uh, they must follow a minimum spacing, okay, between each other. Okay, so now I go back to the PowerPoint. Okay, so all the spacing and then the width that is followed by the layers in the design rules will determine the size, okay, of the chip. Okay, and then the size of the chips, we call it as the feature size. Okay, feature size of a transistors. Okay, okay, a feature size of a transistor will make up a chip, and then the chip, how it is made of, is actually it is being patterned using a set of masks. Okay, so here the statements given, the chips are specified with a set of masks. Minimum dimensions of masses determines the transistor size, and hence speed, cost, and power. The ratios of minimums allowable values of polysilicon gates width and the gate length is called as minimum feature size or minimum transistor length. Okay, so this is a figure that shows the width and length of a transistor. Okay, so this is for the polysilicon. Okay, so polysilicon and then the width here is defined between, uh, not between, okay, it is defined by the width of the diffusion area. Okay, this is the diffusion area. Okay, where these diffusion area are mostly used to form the drain and source terminal. Okay, and then the length here is the length of the polysilicon. Okay, so there is a formula that define the feature size, which is the width over length. Okay, feature size is defined as the width over length. Okay, this one will be mentioned also later further. Okay, so this one is a diagram that shows the feature size for PMOS and NMOS. Okay, so this is a 3D diagram for both of the transistors with the length and then the width. Okay, so from 2002, the length here is 130 nanometer. And then the next few years, the length can be made smaller to 90 nanometer and 65 nanometer. Okay, so the length here is indicate as the length of the polysilicon gate. Okay, it can be made smaller. Okay, as long as the design follows the design rules, then the transistor can be made smaller. Okay, and then by manipulating the width and the length. Okay, especially the width. Okay, later you will see. Okay, sometimes the designer manipulate the width. Okay, okay, some of the website or you see the books, they will mentions differently. Okay, some as I see here, okay, I didn't read a lot, okay, but from what I refer to some of the references, okay, some of them they vary the width, okay, not sorry, no, okay, I want to make a corrections. I think wrongly. Okay, so the feature size they reduce the length. Okay, they reduce the length to obtain a smaller transistor. Okay, width is different. Okay, that is the different case. Sorry, just now I think it wrongly. Okay, so you can see this. Okay, how the transistors is determined. Okay, the size of the transistor. Okay, transistor dimension specified as width over length. Okay, minimum size is 4 lambda divided by 2 lambda, sometimes called as 1 unit. For 0.6 micrometer processors, width is 1.2 micrometer and L is 0.6 micrometer. Okay, and this one, if we refer to this figure, we use this figure. Okay, this figure is the schematic diagram for this. Okay, this is the layout design of the CMOS inverter. Okay, these all are CMOS inverter. Okay, so if I refer to this figure shows that the width over length of the transistor for both transistor PMOS and NMOS. Okay, so as you see that the feature size for PMOS, this is 8 over 2. Okay, and then NMOS is 4 over 2. Okay, and we can reduce it to represent it in this way. It shows that the NMOS, okay, this is NMOS and this is PMOS. The PMOS, the width is actually twice larger than the NMOS. Okay, there is a reason behind why this width of the PMOS is twice larger. Okay, this one this one I will not be mentioned here because I want you to go and find out. Okay, I want you to go and find out. But this is the theory behind. Okay, this is the theory. The PMOS, the width of the PMOS must make twice larger than the width of the NMOS. Layout design rules, sometimes we call it as MOSIS, CMOS design rules. Okay, MOSIS here, you will always see this term, okay, when you start to use the electric VLSI software. Okay, and then the layout design rules that you will be used is actually based on this MOSIS, CMOS design rules. Okay, MOSIS stands for MOS Implementations Service. Okay, it is an IC fabrication service available to university for layout, simulations, and test the completed design. MOSIS Scalable CMOS and CMOS. Okay, if you see this, sorry, just now I say wrongly, is it? Okay, this is S. Okay, S CMOS. Okay, S CMOS means it is scalable. Okay, S here means scalable. Okay, scalable CMOS. Okay, scalable CMOS is a set of logical layers together with their layout design and layout rules, which provide a nearly process and metric independent interface to many CMOS fabrications process available through MOSIS. In its rules, circuit geometries are specified. The units of measurements, for example, lambdas, can easily be scaled to different fabrications process as semiconductors technology advance. Project designs often use lambda-based scalable CMOS design rules from MOSIS because they are simple and freely available. MOSIS offer processors from 2 micrometers to 180 nanometer with scalable CMOS rules and support 3 variants of these rules. Okay, the 3 variants of these rules are the scalable CMOS and sub-M. Okay, this sub-M is mean by the submicron. Okay, this is a submicron, and this is deep. Deep is one of the rules in layout design rules. We call it as deep rules. To take advantage of the advanced submicron processors, the scalable CMOS rules were revised to create a scalable CMOS submicron. Okay, here is a table. Okay, this table shows the scalable CMOS, submicron, and deep rules. Okay, so these three different design rules, okay, they have all the minimum spacing and width required, okay, to follow by all the layers designed in the layout design. Okay, so all are listed here. Okay, later I will show you for the submicron. Okay, since the rules that we will use in the electric VLSI software is the submicron, so I will show you the submicron. Okay, why we use the submicron? There is no reason. Okay, the only reason is the tutorial that uh, I will give you, and also in the previous SEM, Dr. Go give you is actually from our website. Okay, all the tutorials for the lab are from a website, and then the website shows the setting of the design rule is actually to use the submicron design rules. Okay, so in your lab work, so all the design must follow the submicron rules. Okay, so this one is the requirement. Okay, for three different rules here. Okay, for all the layers. Okay, I take one for example according to this table, and then to compare it with the examples that I show you just now, that is with an error. Okay, let me see which one I should take. Okay, poly, I see this poly spacing. Okay, poly spacing to poly over active. Okay, maybe we use this table, we check this spacing of poly to active. This one. Okay, we check this. Okay, according to submicron, this is one spacing of poly to active. Okay, if refer to this example, spacing of poly to active. Okay, you see this? Spacing of poly to active spacing is the minimum is 1. Okay, if follow to the table just now, it is 1. Okay, you can check and compare. Okay, so all the layout design rules here all already stated. Okay, just now I show this one for the spacing of poly to active. It is 1, minimum is 1. Okay, so for other as well, others the spacing is also stated here according to this submicrons design rules. Okay, how do we make the configurations in the electric VLSI software when you want to start to design the layout design? Okay, so this is the configurations that you can make. Okay, the configurations always can be made by uh, going through the preference. Okay, if you goes to the preference, you will see this. Okay, see this, and then you can set. Okay, you can set, and also you can select the setting that you want. Okay, so now I show you the technology that will be used for this design. Okay, so this is under technology. You see this, the layout technology to use for schematic is more CMOS. Okay, this is the MOSIS CMOS technology describe a scalable CMOS process that is propagated by the MOSIS projects of the universities of Southern California. Okay, so we should always select this technology as the more CMOS technology. Okay, and then here there are a few of the design rules here that we can select. Okay, the one that you should need to select is the submicron rules under this more CMOS technology. Okay, for the scalable CMOS rules and deep rules, this is the rules that that are for a more complicated circuit. Okay, because you see that the metals that it can use is actually more than four. Or sorry, not more than four. For scalable CMOS rule, it is four metal. Okay, four metal or less. Okay, for the deep rules, it is five metals or more. Okay, we can select the scalable CMOS rules. Okay, then the spacing and the width will be different. Okay, but by default, the rules that we should select is the submicron rules. Okay, so this is the setting we should set. And then the metal layers here, we also can set it as 4 layers, 3 layers. Okay, if you did not use to up to 3 layers, you can just reduce the number of layers here. Okay, okay, and then after we have set the technology for the layout design, we can also set the scale. Okay, as you see that this is the scale, the choice of the scales that we can select. Okay, with different technology. Okay, since we are using the more CMOS technology, so we have to select this more CMOS setting with the scale 300 nanometer. Okay, what is mean by this? Okay, here explain to you what is mean by this. Okay, if a transistor that is with 2 by 3 in size is actually stored in memory as 2 by 3, then each technology has a scale measured in nanometers to convert this unit to real distance. Okay, for examples, if the scales of the MOSIS CMOS technology is 300 nanometer, mean this is the scales that follow. Okay, then the 2 by 3 transistor is actually 600 by 900. Okay, means that 2 multiplied with 3, then it is 600. This is in nanometer. Okay, in nanometer. And then 3 multiplied by 300, then it is 900 nanometer. We can convert it to micron. Okay, if we convert it to micron, that means that it is 6.3 micron by 0.6. Okay, it is 0.6 micron by 0.9 microns. Okay, so this is how we should interpret the size of the transistor when we design the transistor in the layout design. Okay, there are two approaches of measurements. One is a micron rules, measures at microns resolutions. Okay, another one is lambda rules. Okay, lambda rules are mostly applied by industrial. Okay, it is a simplified micron rules with limited scaling attributes. Based on single parameters lambda, it characterizes the linear features. For example, the minimum grid dimensions and allowed simple scaling. It requires for resolutions of tolerance of the masses. Design rules represents a tolerance which ensures very high probability of correct fabrications. Okay, for submicron rules, all minimum size and spacing specified in microns. Okay, just now I have shown you. Okay, we can convert the size of the transistor in nanometers to micrometer. Okay, so we call it as a micron rules. Rules don't have to be multiples of lambda. can result in 50% reductions in area over lambda-based rules. It is a standard in industry. Okay, some industrial, they also use the micron rules, but then when the technology advance, they prefer to use the lambda rules, okay, because lambda rules is more simplified rules. They can represent it in a simple way. Okay, so this is the figure that shows a micron rules. Okay, the size here given is integer. Okay, it's an integers. Then this is the width of the wheel and spacing. You see that this is integer. We can actually multiply with the scale. Okay, if the scales that we set is 200 nanometers, then we need to multiply the scale with this integer. Okay, as already explained just now to you. Layout constraints are stated in terms of absolute dimensions in micrometers. Industrial uses micron rules to ensure that the circuit builds are as small as possible. However, the layout are not portable and are complex, especially for deep submicron designs. Okay, so now is about lambda rules. Okay, lambda based design rules. Okay, for the just now the micron rules. Just a short introductions to you. Okay, if you want to read more, you can go to find others books or any other website to read. Okay, here I did not provide any further information. It is just an introductions to what is micron rules. Okay, now is the lambda based design rules. Lambda based design rules define scalable rule based on lambda, which is half of the minimum channel's length. Circuit designer in general want tighten, smaller layout for improved performance and decreased silicon area. On the other hand, the process engineers want design rules that result in a controllable and reproducible process. Generally, we find there has to be a compromise for a competitive circuit to be produced at a reasonable cost. All width, spacing, and distance are written in the form K lambda is equals to the 0.5 multiplied with the minimum draw transistor length. Okay, okay, here there is an examples here. Before I show you the examples, okay, there is a further there is statements here for the lambda rules. Okay, scalable design rules as a functions of lambda allows linear and proportional scalings of all geometric constraints. The purpose of designing lambda property is to make the design itself independent of both process and fabrications. Typically, feature size of process is set to 2 lambda. Okay, then if the lambda is equals to 0.3 micrometer in, okay, now is actually, okay, this examples means that if the lambda is 3.03, sorry, this is lambda is equal to 0.3 micrometer, then it means that the feature size is 0.6 micrometer. Okay, why is that? Because here already mentions the feature size is set to 2 multiplied with the lambda. So now the lambda is a 0.3 micron meter. So it means that the feature size is 0.6 micron meter. Okay, I see that we still have 5 minutes left. Okay, I will finish the lambda rules, then I will stop. Okay, let me check again. Okay, so I want to refer back to these equations. This equation is actually the same one with this one. Okay, it's actually the same one with this one. to lambda. Okay, through the lambda, we can obtain the feature size of the transistor. Okay, but we will have to see what is the lambda given here. Okay, so for all the minimum requirement and spacing, all the minimum spacing and width requirement in lambda rules, they are actually stated in this way. Okay, 4 lambda, 1 lambda, 2 lambda. Okay, so if you see any others layout design with the minimum spacing and width stated in this way, so it means that the layout design is actually based on the lambda rules. Okay, so I think I will stop here. Okay, we still have another class at 11:30. Okay, our class is a tutorial class, the next one. Okay, so I think there is no question from you right now. Okay, later when you do the revisions, I hope you will be able to understand back. Okay. Okay, so I think no more that I want to cover today. Let me see your attendance first before we dismiss. Okay, I see that the attendance no problem. Okay, so we can dismiss class now. Okay, so those who will be having tutorial with me later, you need to stay back. The group is group 1. Okay, that will be having tutorial today. Okay, thank you to all of you. Happy Chinese New Year. Okay, remember that there will be no class on Wednesday.